Hi everyone, hope you're all keeping well. It's now time for our next lesson where we're going to be exploring electrical efficiency. So let's take a little look at our learning intention and success criteria. So our learning intention for today is to explore the efficiency of electrical devices, and our success criteria, well, hopefully by the end you'll be able to explain what the efficiency of an electrical device is. So what does that actually mean? And you will be able to calculate the efficiency of different electrical devices. Okay, sounds quite complicated, but it's not too hard. So let's have a look and see how we do this. Before we start, what I would like to just talk a little bit about is rating plates. So this is something we haven't kind of talked about before, but most, not all, electrical devices have this thing called a rating plate. We'll have a look, get a couple of example rating plates in a wee minute. The rating plate is quite important because it tells us a lot of information about that device. So it can tell us things like how much current the device needs, what the kind of power it's going to utilise is, the voltage required by the device, all these kind of useful information, all this kind of useful information. Not always get everything, all of that on it, but it's normally get enough that you could kind of calculate any of the missing values. So it's very, very important that we've got it. And it also allows us then to calculate how much energy the device actually consumes as well every second. So remember, our definition for energy is the amount of power. Our definition for power is the amount of energy used every second. So energy is kind of power times time. So here are some examples of some rating plates. So up at the top here we've got a paper shredder here, and it's got the voltage, it's got the current, and it's got it's got some various other information in there as well that's not necessarily hugely important for what we're talking about. This is just kind of a specific instructions regarding the operation of the device. Here we've got a rating plate from a kettle. So we've got again the voltage, this is the voltage input. We've got a range of powers here, so this is it's going to operate somewhere in this range here. This one doesn't have the current, you'll notice, but if you know the power and you know the voltage, we can go and calculate the current. You can have a look at one of the other lessons to see how to do that if you're unsure. This one here is the charger for a drill. So it's got a little bit more information on it. So we've got an input voltage and an output voltage here, and current. Now, this is important because it kind of links back to what we were doing last time, and that this is basically a big transformer, and the input voltage would be what goes into the primary coil, and the output is what comes out of the secondary coil. So this kind of links back to what we were doing previously. And down here, this is from a big outdoor security light. So again, we've got a voltage, and we've got the maximum power that it can handle. So that would depend on the bulb that you put in there, and that would be the maximum power rating on the bulb that you'd put in. So that's some example rating plates here. Now these are quite important because if we want to do calculations regarding efficiency, quite often we need to extract some of this information or some of this input information from a rating plate. So it's just worthwhile having a little look at them just before we kind of get going with this. So what do electrical devices do? Let's just pause for a second and have a little think about that. What does an electrical device do? Okay, so let's have a look and see what electrical devices do. All electrical devices convert electrical energy, which is input into them, into some other type of useful energy that allows the device to do its job. So some examples of that might include, for instance, a washing machine, where you take electrical energy, you put it into the washing machine, and that energy is converted into kinetic energy, which is the movement, which allows the drum to turn, and heat energy, which heats up the water, and there'll also be some movement in pumps and various other bits and pieces as well. But there's a lot of different energy transformations that are going to happen within a washing machine. Another example would be a kettle. So a kettle, obviously, we use to heat water. So that takes in the electrical energy and it converts it into heat energy, which is what we want. That's a great use for it. Third example, a loudspeaker. So it again takes in electrical energy, and this time it converts it into sound energy. So we can have lots of different energy conversions in different devices, and the device is designed specifically to do a specific job. And actually the loudspeaker, you might find, you might want to include kinetic energy in there for the movement of the kind of cones, which actually creates that sound energy. However, that's neither here nor there. So electrical efficiency, in an ideal world, all of that electrical energy that we put into a device would be converted into something useful. That would be the ideal situation. However, unfortunately, we do not live in an ideal world, and not all the energy is converted into useful forms. Some of that energy is going to be lost to the surroundings. And this is essentially where electrical efficiency comes in, because if we're not getting all this energy converted, how efficient a device is how much of that energy is being used or converted into useful energy, and then of course that kind of leaves you with the energy that is lost as well to other less useful forms of energy. So a couple of examples here for you. When a washing machine is switched on, some of the energy is lost as sound. So if you think about when you turn the washing machine on and it's doing its job, you can hear the drum turning, you can hear the motor running, you can hear all sorts of things kind of happening when the washing machine's on. We don't want to hear it, we don't necessarily need to hear the washing machine, so that energy is lost as sound energy. When the kettle is boiling water, we're also getting unwanted sound energy given off, and there's also a potential for a little bit of heat to be lost to the surroundings as well. But we've got this kind of unwanted sound, and if you're unsure about that one, go and try and boil a kettle, and you will hear the kettle boiling. You don't need to hear the kettle boiling. That's not a function that it's designed to do. It's something that it does do, which essentially results in energy that is lost. It's not energy which is being used in a useful way. So if we know how much energy is input into the device and how much useful energy we're getting out, we can use this information to go on and calculate the efficiency of a device. So let's have a look at that. This is our equation for efficiency. So I'm going to start off with this equation. There's two equations we're going to look at today. Remember, you'll get all these equations when you need them, so you don't need to remember them. So I'll give you this one first of all. The equation here is for energy. So we have the percentage efficiency of the device is equal to the useful energy that we get out of the device. So it's that useful energy that is converted into the useful forms. So in your washing machine, it's the heat energy and the kinetic energy, and the movement of the drum, and maybe the movement of the pumps, and the heat energy that's used to heat the water in your washing machine. So these are your useful energies. So if you kind of summed up all of those energies, you would get your useful energy that's out, we get out of the device, divided by the useful energy in. So that's the energy that's coming into the device, and that's where your rating plate becomes very useful, because that tells you how much energy the device is likely to draw. And then we multiply that by 100. We multiply that by 100 because we are calculating this as a simple percentage. It's as simple as that. It's a percentage efficiency. How much or what percentage of the energy in is useful, are we getting back out in useful energy? That's what we're going to try and calculate. So let me just bring this up, just a little bit of information here. So this is the energy efficiency of a device calculated as a percentage. So in other words, it's a percentage of the useful energy in. This one up here is the useful energy out. So we need to know how much useful energy is converted in the device, and this of course, as all types of energy, is measured in joules. And down at the bottom here we have the electrical energy input into the device. This can often be calculated from the information on the rating plate, and once again measured in joules, as is all energy. So this is our equation. I think at this point in time what we do is we just stop where we are, and we go away and have a look at a quick worked example before we move on. So let's have a look at this, a worked example. Now this one is going to take two parts, take the form of two parts. So we've got a kettle, and it has a power rating of 2,800 watts. Now if you were to look back at the rating plate on the kettle that I showed you, you'll see that had that rating is kind of somewhere in the middle between the range that the kettle was expected to operate at. So our kettle here has a power rating of 2,800 watts. So the first part of the question, how much electrical energy does the device require if it takes 130 seconds to boil. So how much energy, electrical energy, is going to have to be input into the device to boil the water, is what we're asking. It's going to take 130 seconds to do that. The second part of the question here, after the kettle is boiled, the amount of heat energy in the water has increased by 290,000 joules. That's a lot of energy, but it does take a lot of energy to heat up water. So, you need to put in a lot of energy into it. So the amount of energy in the water has increased by 290,000 joules. What is the efficiency of the kettle? So let's take this one step at a time. We'll answer part A. So let's have a look and concentrate just on part A. So our kettle has a power rating of 2,800 watts. We need that information. How much electrical energy does the device require if it takes 130 seconds to boil? So, as with all questions, what's the first thing we're going to write down? Have a little think about it. Feel free to pause here if you want to have a think about it. I'll give you a few seconds. Okay, so for those of you that said we write the equation down first, you're not quite right here, I'm afraid. Remember, we always write our shopping list. We write what we know, what we don't know. So let's start off with that. First of all, we know that the power used by the device is 2,800 watts. We know that the time is 130 seconds, and we are asked to calculate the energy, the amount of electrical energy it's using. So we're asked to calculate the energy. Okay, so now we know what we've got written down, what we know, what we don't know, what we're looking to calculate. Now we move on to our first step, which is, of course, the point where we get our first mark. We write down our equation. So, as I said earlier, power is equal to energy divided by time. It's the amount of energy used every second. Okay, it's the number of joules of energy used every second by the device. Okay, so we're looking to calculate, of course, energy here. We're not looking to calculate power, but this would be the standard form that the equation is normally given to us in. At National 4, just for those of you that are kind of concentrated on National 4, remember that you will get given the equations in the form that you need them in, so you don't need to worry about rearranging. Those of you that are doing National 5, this would be some point where you would need to rearrange the equation. You would be given the equation in this form, and you would then go ahead and rearrange it into the useful form later on in this process. However, before we go and rearrange the equation, we of course want to substitute in our numbers. That gets you your second mark, and if we do the rearrangement first and then substitute in our numbers, but we make a mistake in the rearrangement, then we lose that second mark because we've made a mistake. Whereas if you put your numbers in now and then do the rearrangement, then we get that second mark, and basically that's good news for us, because we've then got ourselves 2 marks just by simply copying information that's given to us on the page. So put in our numbers. So we've got 2,800 watts, so it's just power being replaced by 2,800, so power replaced by 2,800. Time is 130 seconds, so 130 seconds here, and of course we don't know what energy is. That's got the question mark next to it, so we'll just leave energy as it is. If you are more used to working with these equations using their letters, do feel free to go ahead and extract the equation from the relevant equation sheet, and you can kind of work through it using the letters and the symbols rather than the full words. I'm kind of using the full words here, just so that to make sure everyone understands where we're going with this. So at this point, what we want to do is rearrange the equation. So I've got 130 on the bottom here that I want to get rid of it. So this is remember the line here means divided by, so get energy divided by 130. If I want to get rid of this, I need to bring it over to the other side, but instead of being a divided by, we need to do the opposite function. Remember, the opposite of a divide is a multiply. So when I bring this 130 over here, it's no longer a divide, it becomes a multiply. And then I'm just going to do a quick rearrangement when I do that, and we end up with the equation in this form here. Energy is equal to 2,800 times 130. Nice and easy. Okay, so we've now got the equation in a form that we can solve, so I'll let you guys go ahead and plug that into your calculators and see what answer you come up with. I'll give you a few seconds to do that. Okay, let's have a look and see what do we come up with. So the answer I came up with here, energy is equal to 364,000 joules. It's a lot of energy that kettle is utilising in order to boil the water. However, I'm not going to leave this as my final step. I'm going to go one step further and I'm going to give my answer as 360,000 joules. Why do you think I've done that? Well, it is of course because we always want to try and give the answer to our questions to the same number of significant figures that's in the question. So in this question we're quite lucky. We've got two significant figures here, so that's 1, 2, and we've got two significant figures here, so that's 1, 2. So I want to give my answer to two significant figures, which brings us out at 360,000 joules. Okay, if we had a different number of significant figures, so let's say if we'd had 3 significant figures here and 2 here, then it would always be 2 because I'm going to pick the number that's got the least number of significant figures, the smallest number of significant figures to give my answer to. Let's have a quick look at the marks though, because if you didn't do that final step, don't worry too much about that in this question here. So first mark here obviously for our equation, we've written down our equation, we get our first mark. Second mark here for substituting in our numbers, getting them in the right place. We've then rearranged the equation. We don't get a mark for that, but it's an important step. And then of course we get a mark for our final answer, including our units. Now in this case here, we are allowed to give our answer to three significant figures, as well. So that is absolutely fine. If you've used either of these answers as your final answer, you would have got the full marks for this question. So don't worry too much if you haven't gone ahead and done that final step and just rounded off that answer, okay, at this stage. Right, so that is part A. Let's have a look at part B. After the kettle is boiled, the amount of heat energy in the water has increased by 290,000 joules. What is the efficiency of the kettle? So this is just immediately on completion of boiling, so there's not going to be a huge amount of energy lost to the environment or anything. The water's not started to cool down yet or anything like that. So again, I'll ask you this, hopefully we get it all right this time. What do we write down first here? Hopefully you've all managed to get it right this time. We do of course write down our shopping list, so I've just brought this all up in a oneer here. Energy in is equal to 360,000 joules. Remember, that's just what we calculated in part A, so we just go back to part A to find that number there. If you've used the 364,000 joules, the answer to part A was, that's absolutely fine. You could bring that, if that was your final answer to part A, you could bring that one forward as well. I'm using 360,000 joules because that's the answer I gave for my final answer. The energy out is given to us in the question here. So I've got 290,000 joules. 290,000 joules. What is the efficiency of the kettle? Well, that's just what we're trying to calculate. So the percentage efficiency just gets a little question mark. So let us do what? Hopefully you'll all have got this one. You'll write down your equation first of all in order to get yourself your first mark. So remember, the percentage efficiency is equal to the energy out divided by the energy in multiplied by 100. Nice and easy. That's just copying that out from the list of equations that you'll be given. So no need to even worry too much about that. It's just copying out the equation. Nice and easy. What do we do next? Hopefully you've got it. We're going to plug in our numbers. So let's have a look. The efficiency is equal to 290,000. So that's just our energy out here with 290,000. So we're going to pop that in the top there. Divided by the energy in, which was 360,000 joules. So 360,000 here. And then the multiplied by 100 just stays as it is. And that's absolutely perfect. Now, no rearrangement here. This is nice. We've got the equation in exactly in the form we need. So you can go ahead and plug those numbers into your calculator. Do remember, if you are going to do 290,000 divided by 360,000 then multiply it by 100, can sometimes be worthwhile just pressing equals in between these steps. So do the kind of first step and then press equals and then multiply by 100, just depending on how your calculator works. Sometimes calculators work slightly differently and you can get the wrong answer just by not pressing equals in between. So try that just now. Okay, hopefully you've all came up with this answer here. Something which goes 80.555 ... That just means that the number kind of went on for a wee bit. So 80.555%. Now, in this case, we do need to rearrange the equation. Sorry, we do need to round off our equation if we've got more than, well, let's have a look at the numbers that we're given here. So we've got 360,000 and we've got 290,000. We're wanting two significant figures again here. So we need to give our answer to two significant figures. If we give it to any more than, if we gave it to this number of significant figures, we would lose our marks. So if we were giving it to five significant figures, we would lose our final marks. We're going to have to round that off. So let's round that off. So 80, remember 0.5, we're just going to look at this one here. This one here, 5 and above, we round up. So it's going to go to 81. Yeah, 81%. Okay, so simple as that. Nice and easy. Any questions at this point? Feel free to pop them in the comments. We can make a private comment somewhere if you feel more comfortable doing that. That's not a problem as well. If you've not, let's continue on. We're going to have a look at the second equation. It's very, very similar. It's not too much more difficult. Sorry, before we do that, let's have a look at our marks. So our marks here, 1 mark again for our equation. As always, we write down our equation, we get our first mark. Substituting the numbers in the right place, we get our second mark. And of course our final answer, and this time we do have to round it, so I've made sure that's down nice and low. We do need to round that one off to get that final mark. If we'd given this as our final answer, we would have lost that final mark. Remember, it's a percentage, so you need to give your percent sign. That kind of becomes your units in this case. So let's have a look at our second equation then. As you can see here, it's very, very similar. This time we've got percentage efficiency is equal to the useful power out divided by the power in multiplied by 100. It's very, very similar. We're just going to use power instead of efficiency. So let's have a little look. The efficiency of a device is calculated as a percentage. This is the power efficiency, of course. So it's a percentage of the useful power in. Here we've got the useful power out, so we need to know how much useful power is coming out of the device. So how much useful power are we getting out of there? And as always, power measured in watts. And down on the bottom here, the electrical power input to the device. This is often given on the rating plate. If not, you tend to generally have the voltage and the current, and you could then go ahead and calculate the power from the information given on the rating plate. So that again brings you back to that rating plate, and the rating plate is quite useful. Let's have a look at another worked example. A little bit simpler this time, only one part. A kettle has a power rating of 2,800 watts, so we're using the same kettle as before. If the power output, so this is the useful power that we're getting out, is 2,255 watts, what is the efficiency of the kettle? Okay, so first thing, it's our third time, so hopefully we'll all get it right this time. What's our first thing we're going to write down? Hopefully you've got it. We're going to write down our shopping list. So the power in is equal to 2,800 watts. The power out is equal to 2,255 watts. And of course the percent efficiency, well, that's what we're looking to calculate. So our next step then would be hopefully you got it. We're going to write down our equation. So we've got percent efficiency is equal to the power out divided by the power in multiplied by 100. Nice and easy. Okay, next step. We're going to substitute in our numbers, aren't we? So the efficiency is equal to 2,255 divided by 2,800 multiplied by 100. Again, nice and simple. The equation's in the form that we need, so I'll let you guys plug that into a calculator. We'll see what you come up with. Okay, so hopefully you've all come up with this answer. The percent efficiency, 80.535 ... So that kind of went on a wee bit. Again, we're going to have to round this off here, so let's have a look and see just exactly how we're going to round this off. So we've got 2 significant figures, and 1, 2, 3, 4 significant figures here. So we're going to pick this one because it has the smallest number of significant figures and give our answer to 2 significant figures. Okay, this is a rule across all the levels that you're likely to work at in SQA. You try and give it to the same number of significant figures as the number that you're given in the question that has the smallest number of significant figures. Quite a complicated way of saying it, but basically it means that we're going to pick this one here. And that's the same, National 3, National 4, National 5, higher, advanced higher, any of these levels you will always do the same thing. So this is a good habit to get into at this stage in time. So let's round that off, and of course we come out at an efficiency of 81%. Dead easy. Again, let's have a look at our marks. So first mark for our equation, we've written down our equation correctly, so we get our first mark. Second mark for substituting in our numbers, perfect. And then our third mark, once again, we are going to get our third mark for writing down our rounded answer again in this case. And again, the percentage sign is basically our units here, so make sure you remember that. Okay, so that's us. If you get any questions at this point, you're unsure about something, there's 2 things you can do. First of all, you can go back through and watch this video again. I will put the PowerPoint up separately so you can kind of refer to specific slides if you want to go back and kind of look at something specific. So a couple of options there for you. And if you're still not getting it, comment below, send a private message. You can send an email through Google Classroom as well. That's absolutely fine. And we will get back to you and we will give you a hand and make sure that you understand how to answer the questions. Okay, in the meantime, you are going to have a go at some questions now. So I'd like you to go to the Electricity and Energy question booklet, which you'll find on Google Classroom. Try the following questions. So it's page 40 to 47, and you're going to answer questions 1 to 15. So that's quite a lot, okay? But work your way through that. Do remember to check your answers as you're going. Make sure that you do it as you're going. You're better rather than doing the whole lot and then going through and then checking your answers. Do a couple of questions, check your answers, because then if you're getting something wrong, you can correct that quite quickly, whereas if you've gone through and done them all wrong, then you find out you've done them all wrong, and you maybe need to go back and do everything again to make sure that you understand how to get it right. Okay, so that's why I always recommend checking your answers as you go. If you need help, ask. I've already said it, but just ask. If you find you're trying to answer these questions, you're coming up with the wrong answer, again, pop a comment on Google Classroom, a private comment, public comment, whatever you want, and someone will give you a hand. Someone will be able to kind of point you in the right direction and hopefully get you able to answer these questions successfully. Next week I will ask you to submit one of the questions just to check that you've understood kind of what we're doing and make sure that you've kind of made the progress that we're hoping you've made through this lesson. Okay, so finally, our success criteria. So if you manage to answer these questions correctly, let's see if we can tick these off. You'll need to kind of go through and obviously do this for yourself. I can explain what the efficiency of an electrical device is. Can you remember that? Have a think about that just now. Try and remember that definition. If you can come up with that definition, brilliant, well done. If not, go back and have a look at it in the slides. Have a watch at the video again. See if you can manage to clear that up in your head. I can calculate the efficiency of different electrical devices. Well, hopefully you managed to do that in the questions. Again, if not, you'll have asked questions by now, and you will hopefully be able to answer these questions. And that's us. So I'm going to leave you with that just now. So have a go at these questions. Ask if you've got any questions. If you're unsure about anything, make sure you're asking questions. I will, as I say, I'm going to ask you to submit one of the questions next week just to get an idea as to how you're getting on, and I can give you some feedback as well. If there's something that you're kind of maybe doing right that isn't quite perfect, that we could just tidy up a little bit, or something that's almost right, I can kind of nudge you in the right direction. We can just get things just nice and tidy, hopefully, over the course of the next week. And so as I say, I'll leave you there. Hopefully you guys will keep yourself safe over the next week or so, and well, hopefully we'll see each other fairly soon.